Let's suppose that we are going to continue with our example where we are in a manufacturing situation producing thousands of parts each day, where 90% are of good quality, 10% are defective, but this time we're going to choose 3 for testing. Again, let's let x equal the number of good parts that are selected. Let's build the tree again. First selection, we could get a good or a defective part. Second selection, we could get a good or a defective part. Third selection, we could get a good or a defective part. Now let's construct a table where we have the number of good parts selected, the number of ways to get X good parts, the probability that we would get that number of good parts. So this is just like a probability distribution, but we've added a column here where we're putting the number of ways that we could get those good parts. So x could take on the value of 0, x could take on the value of 1, x could take on the value of 2, or x could take on the value of 3. I'm choosing 3 this time. So I could get 3 good ones, x is 3. There are several ways that I could get 2 good ones, and I have to keep in mind that if I have 2 good ones, I'd have 1 bad one. There are several ways I could get 1 good one. If I have 1 good one, then I have 2 bad ones. And then there's only one way that I could get no good ones. That would be where I have all defective. So we'll put a 1 here and a 1 here. Now let's see how many ways I could get 1 good one. I could either follow the branch that goes good, defective, 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 good, defective, or defective, defective, good. So that's 3 ways. The number of ways I could get 2 good ones would be if I followed the branch good, good, defective, or good, defective, good, or defective, good, good. So there's 3 ways to do that. Now if we count the number of ends of the branches here, we've got 1, 2, 3, 4, 5, 6, 7, 8, and there are 8 ways accounted for here. And the thing that we have to keep in mind here again is that we're producing thousands of these items, and then the probability that we would get a good one is going to remain consistent. It'll be 90% if we're choosing 3, even though we're not putting the back. And the probability then that I would select a good one remains consistent at 0.9 all the way through this tree. And the probability of selecting a defective one remains consistent at 0.1. So I could just fill in all these branches here with these individual probabilities. And here we see then the probability that we would get no good ones, the probability that x is 0. Well, that's this branch that has all defective, and that's going to be 0.1 cubed. Three ways to get 1 good one, and no matter how I do that, I'm going to have 1 good one and 2 defective ones, which gives me a 0.9 and 2 0.1s. So we'd have 3 times 0.9 times 0.1 squared. And I'm just going to, just for the sake of a later discussion, I'm going to put a 1 exponent up here. And then we have 3 ways that we could get 2 good ones, which would give me 3 times 0.9 squared times 0.1 to the first power. Again, any one of these branches that has 2 good ones, I'll have 2 0.9s and 1.1. And then there is only way that I would get 3 good ones, and that's the top branch here, which would be 0.9 cubed. And again, I might put this understood 1 here and multiply it out front.